Hey guys, welcome back. Got some cool stuff for you today. Today we'll be continuing our simulation of the binomial model. Also be getting into the Galton board. I'm going to show you that. I've actually got a Galton board. I think I've shown it to you at the beginning of school, beginning of class, maybe if we were ever in person. I have no idea, but next time I see you guys, ask me to get out my Galton board and I'll let you play with it. It's really, really cool. I've actually got a video that is mesmerizing, absolutely gorgeous from the manufacturer that I'll show you guys as well. We're going to be getting into PhET simulations, which are pretty awesome if you've ever done physics before, but they have some a Plinko probability board that we're going to be going into today as well. And then, yeah, just diving into simulating the binomial distribution. So beautiful stuff, wonderful day. It's really late. Oh my gosh, it's 2 o'clock in the morning, but I'm excited. Let's do this. All right, so we have geometric model and the binomial model. So the geometric model here is basically modeling out how many trials till we're expecting our first success. So the most probable is always the first one, because everyone after that requires, and it would just be P, everyone after that requires a probability of a failure to have occurred before that happened. So they'll always be skewed to the right. The PDF will give us individual probabilities there. CDF will always go from the left bound. Then the binomial distribution says out of a certain number of trials, how many successes are we expecting? And that one will, unless our probability is 50-50, like a coin flip, it'll always be skewed. However, if we increase the sample size large enough, like we'll see today with the binomial distribution, then it can be approximated by a normal model, which we'll talk about more when we're back in class on Monday, which will be wonderful. And then we're going to do a lab with a casino lab as well when we come back on our second day. So all of next week should be pretty exciting. I'm excited. All right, so Bernoulli trials, again, is the basis for both models, the geometric and the binomial distributions, and it means we have to have two possible outcomes, probability of success and failure. They have to add up to one. There's only two outcomes, and they must be independent of each other. The geometric model tells us the probability of our first success, so we can model that out using our applet, which is really nice. The individual probabilities from the PDFs would be like the probability on the first one would be our first success, the second one, the third one, etc. The CDF would take the area under the curve and add all those together for you, which would be very nice. So here's our CDF for the first three, just all those PDFs added together. So again, just add together, kind of nice. All right, then we have this thing called Pascal's triangle. This is actually the binomial expansion. So if you take two binomials, and you expand it by some coefficient, the coefficient will tell you the row that we're on in Pascal's triangle, starting at row 0, which would be just one coefficient. And these coefficients are shown here. So 0, 2, 1, or sorry, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. They're all shown here, which is lovely, very, very interesting. And so because the binomial expansion is the same as the binomial model, I mean, it's from the same name, essentially it's telling us all the combinations of probabilities of getting there. Then the only other thing that's at play is whether or not the distribution is equally as likely, or if it's going to be skewed in one direction or in the other. Oh, die on the inside every time I have to say one direction, but and we'll get into that with our Plinko probability as well. So let me show you just a few patterns that are in Pascal's triangle. So you've got your ones on the first column here, then counting numbers, just integers, whole numbers there, and then triangular numbers, which are shown here. Triangular numbers are numbers that you can form triangles out of, essentially. It's also like the factorial, but we're doing addition. So 1 plus 2 would be 3, 1 plus 2 plus 3 would be 6, 1 plus 2 plus 3 plus 4 is 10, 1 plus 2 plus 3 plus 4 plus 5 is 15, 1 plus 2 plus 3 plus 4 plus 5 plus 6 is 21, etc. So those are counting numbers. They show up in some pretty cool places, by the way. I've seen it personally in a few things that I've gotten into where I've needed basically like an addition version of factorial, which is just triangular numbers. Also, triangular numbers show up, yeah, in lots of cool places. So I'll just leave it at that. So anyway, then the next one we have is actually, I believe, Fibonacci sequence goes diagonal, I believe. Let me see if I can go to that one here. Yeah, so the Fibonacci sequence is if we add these diagonals here, so that'll actually give you the Fibonacci sequence, which is actually really cool. So let me show you, let's do our Plinko probability lab first, and just as an introduction to binomial expansion, and then we'll get into, I'll show you this Galton board, which I have one, and I'll show you the video for it. So let me, I think it'll show everything, so let's do the lab, and you've got you've got a link to this. I put it on the classroom here. So this is Plinko. Every time that a ball hits one of these pegs, it has a 50-50 chance, if it's balanced, right, for it to go left or for it to go right. So let me drop one of them and we can just watch what happens. And so it has an equal probability of weights of left and right. Let's drop another one, see what happens here. Whoa, that was really odd. We had a bunch in a row that all went to left, like 6 in a row. You can also think of this as like flipping a coin, and each time we hit a peg, it's like another event. It's like flipping another coin. So that would have been like having 5 tails in a row if left was tails and right was heads. So let's do 10 of them, see what happens. What's kind of cool is that each one of them, again, random. We can't predict the outcome of where any one of them are going to go, but we will notice a pattern start to form in the long run. There'll be a distribution or a shape that is, whoa, there's some rare ones. Oh, wow, that was like seven tails in a row or whatever. It's very rare. There's not many out there on the tails. Most of them are actually falling in the middle. And the reason for that is because there's the most combinations that we could get would be equal combinations of left and right. And so the more lefts that you have, the fewer combinations that would be there. And we can actually see the total number of combinations in the Plinko board. So let me show you a video of this happening with the Galton board so you can see it. They will have 500 BBs that drop pretty well instantaneously. They do it slow-mo, and it's like super, super cool. So let me show you that. So we'll roll that clip real quick. All right, so what's really cool here is that this binomial expansion is telling you the number of paths that BB could travel every time it hits one of the pegs. By the time we get to the 11th peg at the end, there are 462 possible combinations of paths that could get it to the middle two. Then 330 to the one to the left, 165 to the left of that, only 55 combinations that would end up here, 11 combinations that would end up here, which means one of them went left, but the rest of them all stayed left. One of them went to the right, but all the rest of them stayed left. And there's only one possible way that it could end up here, which is if it hits left 11 times in a row, right? It should make sense. Same thing going on the other side. So if we add these all together, we can find the actual probabilities. And what's cool is as we increase the number of trials or the number of 11 coin flips in a row, if we do 26, which we'll be able to show on the next one, this will approximate a bell curve perfectly, which is really, really cool. Another thing is if it's level, it's equal to go left and right 50-50, but we can actually tilt it to the side and make it favor one going left or going to the right by just using gravity, and we can actually produce a skewed distribution, which is absolutely amazing. And I make a joke that, you know, it's like I skewed it all up, get it, like screwed it up, but I skewed it up. I know it's a bad joke. It'd be better in person, wouldn't it? Or if I actually had my Galton board with me, but that's okay. So the next thing I want to show you, and you can actually do this, is we'll go into the lab here and we can change the number of rows. I believe in the Galton board there's 11 rows, so this is like exactly the Galton board we have. And I'm going to make the binary probability equal, and then we're going to see what happens. So here we have all the balls dropping here, and it's going to graph out the distribution for our simulation essentially as we go. Now the Galton board has 500 BB, so it goes really, really fast. I can actually make this go faster if I do the path, because then it doesn't have to graph all of them. You can see the number increasing much, much faster, but you can see all those individual paths that are forming. And again, we said there was I don't remember exactly how many. I guess I'll pull it up again. There were 462 paths that could get us to the two that are in the middle, and only one path over here, 11, et cetera, et cetera. So if we continue the Pascal triangle for 11 rows, it's going to get really, really big really quick. And what's cool is we can see that that is approaching this normal model as our sample size increases. So here's, we're over 500 BBs, so this would be like one set, and then you could reset it, and you could do it again. It'll be very, very similar. What I want to show you, which is really cool, there's a reset button here. So let's go to 11 rows, is what if I change, and I'm going to show you the ideal, what if I change the probability? So I make it where it's not equally as likely. Like for instance, probability of getting a LeBron James card, right, which was 20%. So now notice that this is going to be skewed to the right. Okay, we have a hard left bound on the left because we can't have any fewer than 0 out of 11 cards. But what happens is as I decrease the number of rows, our distribution gets more and more skewed. Remember when we did out of 5? This is actually the binomial distribution for out of 5. And each time we hit a peg, you see how the pegs are tilted? That is so cool. That's making it favor one side. Oh, that is so awesome. That makes me so happy. Okay, this is definitely a lot of fun to play with. But it will go to a binomial distribution here. But what's cool is that our binomial distribution, let me hit the reset button, as we increase the number of trials, let me show the ideal. As I increase the number of trials, let me go back to 0.2, so it's skewed to the left. All right, so we started out with 5. As I increase the number of trials, watch how that reforms into a normal model. So it looks pretty unimodal and symmetric at this point. As I go all the way up to 26, even the most skewed distributions will become more nearly normal. And that's the central limit theorem. By central limit theorem, it's like the central idea or concept behind all of inferential statistics, or which we would just say statistics in general. So the most important or central idea behind all statistics is that any shape of distribution, when sampled from with means or proportions, will become more nearly normal and can be approximated by a bell curve as our sample size increases, which is fascinating. Absolutely really cool. Anything else that I want to show you on this one besides all the so this is just really cool. Let me show you all the balls, and then we can watch and we can see, oh, you divergent, look at you. Oh, oh, this one's gonna beat it. No, it didn't. No one has gotten past that bound. Oh, except you. Okay, yeah, how exciting. Yeah, absolutely amazing. We could also do where it's rigged. Is it a fair dice? I don't think so. Okay, I should stop playing. You should play with this on your own. It is really, really cool. Really, really cool. All right, we will definitely revisit that whenever we come back to the central limit theorem, but it's the binomial. It's so stinking cool. I hope you enjoyed the Gallatin board. You can play with it when we get to class. Just I'll definitely bring it out whenever we're back in class. Okay, so cool stuff. Anything else? I don't think, yeah, there's so many things, so many patterns in the Pascal's triangle. It is so stinking cool. So let's simulate our own binomial distribution. So we've already done the first 40 trials. We did that yesterday. So here's what we got for that. None of them had 4 or 5 out of them. Let's do the next 30 trials. So we're just going to increase it and see what we get. So this one had 0, this one had 0. We had 1, 2, 0, 1, 2, 1, 1, 0, etc. So you can do that, and then what we want to do is we want to go ahead and add the total number of zeros. I guess I'll do it real quick. It's not going to take that long. 2, 2, 1, 2, 0. It's really easy when you color code them. I made yours bold, but if you're not doing it on the iPad, you won't be able to see the color. I guess there's a benefit of the iPad in there. Okay. All right. So how many zeros are we adding to the first 20 trials? Looks like 1, 2, 3, 4, 5, 6, 7, 8. So 8 more. So altogether, so there were 8 on this one. How many ones do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All right, so 12. How many twos? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 twos. How many threes? I don't think we had any threes. no 3s, no 4s, no 5s, and a total were 30 altogether. So let's add the frequency for the first 70. So add them all together. So 24, add those would be 26, 19, 1, 0, 0, and then a total of 70. Now let's find the estimated probability for the binomial we're simulating, right, for the first 70. So for the first 70, basically we're going to do 24 out of 70, which is going to be that fraction, and then 26 out of 70, 19 out of 70, 1 out of 70, and then zeros for the remainder. And that should add up to 100 if we did it right. And this is the true binomial. So this is just a sample size of 70, and it's not like we did 50 BBs. That would be really cool. Which is just so amazing about the Gatlin board is that it does it like instantaneously. I mean, this is really painstaking to do it, but this is what we're doing. I mean, we're rigging one with a probability of 0.2 with 5 rows on it, and we're running simulations to see how many random integers that we would get that were in certain combinations. So 0, 1, 2, 3, 4, all the way to the 5. But this one was so skewed to the right, I can't stop talking about it. I'm gonna have to bring it back up. All right, so let me show you what we were actually doing. So basically we had 5 rows, we had a probability of 20%, and we were running this simulation. Then it was very rare to have any of those, and so we did a simulation of 70, I believe. And we're approximating the normal model. Oh, so close. Oh no, I messed it up. Okay, I think it'll actually show me the counts, or I can tell it to give me the probabilities. It's so cool. All right, so here are the probabilities that we got from this simulation of 70. Compare that to the probabilities you got. And the actual binomial distribution is the ideal, which is in the blue there. Now, if we increase the sample size, which ain't nobody got time for that, we got homework, right? Then eventually it would approach the binomial distribution, like the actual model itself. So cool. So cool. Don't worry, I'm not going to make you simulate 204. We just did it there. Okay, I'm done. So awesome. All right, so compare. How far off? That was close. That was really close. That was pretty far off. We had a lot less than we expected of 3s. We should have had about 5%. We only had one altogether, really. And then these were less than 1%. So the fact that we didn't get any, we would have expected to have to do at least 100 before we got our first success for those. Okay, so really cool. Even with a small sample, we were able to approximate the binomial distribution fairly well. All right, so did our simulations improve by running additional trials? Yes, it did, I believe, if we compared the two. So if I compared our first estimate to our second one, so it actually got better. That one got better as well. This one improved. This one got worse, but that's because we didn't get another one, and those stay the same. So yes, it did improve, but it's not guaranteed. I mean, any short-run behavior, we don't know. There can still be some crazy amount of variation going on and stuff like that, but in general, we would expect it to improve in the long run. All right, did our estimations improve by running additional? Yes. What was the expected value? The expected value for us in 0.2 times that would be 1. So 0.2 times 5, I believe, is 1. Was the binomial distribution symmetric? No, because it's skewed to the right, because we're always, because our probability was not 50-50. We can see that here, even with small samples. Let me pull this back up. So even with small samples right here, if our probability is 50-50, then we're equally likely to have one more or one less than the expected value. So pretty simple, and I think it actually will tell you the mean as well and the standard deviation, which is awesome. Was it symmetric? No. Is it more probable to have one less success or one more success? Well, if a probability is 0.2, it's less than 0.5, so it's more likely to have one less than one more because the probability was less than 50%. That's why it's skewed to the right. All right, example 1, and then unfortunately we're almost done. This will be a short video, and like awesome video. Greatest, most fun day ever. Until we do central limit theorem, we'll revisit this stuff. The American Red Cross says 11% of the U.S. population has type B blood. How many donors on average should the American Red Cross expect to collect until it gets a donor with type B blood. So that's the geometric probability. So our geometric distribution, how many until our first success. So remember the mean for that, the average is going to be the reciprocal of 0.11. So 0.11 to the -1 power. I'll show you again how to put that in the calculator. So 0.11 and then to the -1, it's got its own button, is 9.09. So on average, we're expecting to have to draw blood from 9.09 people before we find somebody who has type B blood, which is pretty rare. What's the median? Okay, so to find the median, we're looking for the 50 percentile. So that's when we would expect 50%. So the mean is actually going to be different than that. So we're going to measure the CDF. I think the easiest way to show this is actually with the geometric distribution applet. So let me pull that up here. So our probability of success was 0.11. And our expected value they were telling us was, well, they're saying 8.09, but that's because all this is off by 1. So that's fine. All right, so I'm going to do 8. And then, so if I measure it from the left, that'll tell me the percentile, right? So the percentile for the mean, the average was a percentile of 64 or 65%. Now, if I want to find the percentile that's the median, that was the 50 percentile. So I'm just going to decrease this until I find a value that's close to 50%. It's really this is the only way to do it, honestly. It's kind of weird, but it works. All right, so 5, which remember they started at 0, so 5 is actually 6. So the median amount that I would expect, so 50% of the time I would expect to find the person, our first type B blood within the first 6 people. But the problem is that after that it could be much longer than that, right? And so our distribution is skewed to the right, which is going to pull the mean or skew or basically pull the mean to the right with it, following that tail. And that's why our mean of 8, or what it was really 9, is going to be much higher percentage. So 65% of the time it would have happened before the mean, which is kind of weird, but you could have those rare occurrences when it takes a long time before you actually find one. So that's why there's a difference, a discrepancy between those two. All right, what's the median number? Okay, so you can also just put the geometric CDF for 6 in and put it in the calculator. That's how I actually originally did it, and then just start plugging in values until you find the one you're looking for. So distributions, we're going to do the geometric CDF. Probability of success was 0.11, and I started out with our mean, which was 9. Okay, which is 65%, and then I changed this to 8, and then I changed it to 7, and just going back with the CDF until I find one that's close to 50%, and then I'm going to call that the median. Okay, cool. So that's where I got 6 as the median. Why is the mean larger than the median? Because the mean is skewed to the right. The whole distribution is skewed to the right. What's the probability that the 10th donor will be the first one with type A blood? Well, that's the geometric, right? For probability of the first success was the 10th one. So, but I'm not looking for a range of values, but just rather one. So that's going to be the geometric PDF. Our first success was the 10th one, and that's going to be basically 3.85%. So geometric PDF, 0.11, first success 10, which is 0.0385. What's the probability that exactly 2 of the first 20? Okay, so this is the number of successes out of 20, which is a binomial distribution. We're doing the binomial PDF because we know exactly 2, not a range of values like less than 2 or more than 2, or at least 2, which we'll do next. So binomial PDF for exactly 2. We'll put that in the calculator real quick. So variables, binomial PDF. Number of trials, we're doing out of 20 trials. Probability of success is 0.11, and we're looking for exactly 2, which is 28 point something. All right, 28.22%. What is the probability at least 2? So at least 2 is 2 or more. So and our CDF always measures from the left. So the only way to do that is to find the probability of 0 or 1. So the CDF measure the 1 and subtract that from 1. That'll give us everything that's left over. Let me show you that real quick so you can see what I'm doing. So that's why it's nice to be able to put this in here as well. So it was out of 20 again. Let me double check. Our probability of success was 11. Let me check here. Yeah, so out of 20, probability of at least 2. So what we really want to do is x is equal to 2, and then we want to measure this from the right. But the problem is our calculator only does CDF from the left. So we need to find the probability of 0 and 1, the CDF up to 1, and then subtract that from 1, and that'll give us the leftover part here. So that's how we're going to have to do it with the calculator. All right, so that's how we're going to have to do it with the calculator. So let me pull up the calculator here. We're going to do second distribution, binomial CDF. We're doing 20 trials, probably a success of 0.11. We're going to go to the first, because that's the first one we're excluding, then hit paste, and then subtract that from 1. So 1 minus that probability, and that gives us exactly what we got from the binomial, which is pretty cool. All right, how many of the first 100 donors would you expect? So 100 times 0.11 is going to be 11. So just to find the expected value, just do n times p. So out of 100, 0.1, which is going to be 11 people. What's the probability out of the first 100 donors you'll find 30 or more? So let me actually graph this one out so you can visualize it and see what's going on first. That way we can make sure that our answer actually makes sense. Binomial. Okay. So now we're increasing this. Also notice, hey, look, this is still skewed to the left. But once I increase this to 100, it's not skewed anymore. Now it's more nearly normal. Now it is slightly skewed because that one's slightly less, still favoring to the left. But as we increase the sample size, it's going to go, we can approximate this with the bell curve, no problem. So look at that, 0.9998. Oh man. All right, so we want to know the probability that we have more than 30. Which 30 is so far out here. I mean, if this is a standard deviation, it looks like 1, 2, 3, 4, 5, 6. It looks like 6 standard deviations. You can actually find it from here. So if our mean was 11, that's basically 19 is our deviation divided by 3, which is going to be close to 6 standard deviations above the mean, which is not going to happen. That's a statistical 0. So let me go ahead and put that in the calculator so you can see how we would have gotten it with the calculator. So basically we're going to do 1 minus 20. We got to go up to 29 because we can't measure from the right. Okay, so 1 minus the 29. So second distribution, normal or binomial CDF. Out of 100 trials, we want to know up to 29. And then we subtract that from 1. So 1 minus that previous answer, which again is going to give us really, really small. So 2 with 6 zeros in front of it, essentially, when we subtract. Okay, so it's a statistical 0. It's not going to happen. 6 standard deviations above the mean, very, 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 very rare. It's not going to happen. All right, I think we're done. All right, we are done. I hope you enjoyed that. That was so much fun. Have a good weekend, or whenever you're watching this, enjoy your Wednesday. And whenever we come back, we're going to do fun stuff. Yeah, we've got a casino lab coming up, which will be really fun. We'll get to play cards and dice, and then we also have other fun stuff. So the Galton board. So I'll see you guys later. I hope you have a good one.